Welcome to those of you who have tuned in. We'll be starting in, let's see, 3 minutes. Good morning, Jonathan. Did you turn in your assignment? Why am I asking? I can check. Hi, Alon. Jonathan, you did turn it in. Thank you. Okay, fantastic. It's not surprise, Jonathan. Why do you say that? I wasn't trying to imply that you usually don't. That was not my intention at all. Hey, Ethan. I got another minute, and then we're just gonna get right on to it. Aaron, back with exclamation mark. I like it. Alanis, hello. Ali, hi. Dahlia, that sounds delicious. Oh no, your dog must be broken. Oh no. I read that somewhere. It might be an urban legend. Let me just make sure I didn't give you guys false information. Huh. No, it was a real study. Yeah. Over 2 years, 70 dogs made up of 37 breeds, 1,893 defecations, and 5,582 urinations. Researchers found that under calm magnetic field conditions, dogs preferred to excrete with the body aligned along the north-south axis, avoiding east-west together. Interesting. Well, I mean, I guess your dog's broken. If birds do the same thing, Ethan, you should record every time they... Well, actually, Ethan, they probably don't, because you know how birds poop? Birds poop, they don't even control when they poop. It just comes out when it wants to come out. Like birds can't hold it in or anything, right? They'll just be tweeting and flapping their wings and something, whoop, it just comes out, as if it was like no big deal. And a lot of birds even poop while they're flying. And yeah. Yeah, a lot of animals will poop when they're scared. Why are all your dogs broken? Okay, it is 11:22. I know in my last email I said 11:20, but the email before that I said 11:25. So let's make it 11:23. Because it took me a lot shorter to fix the camera than I thought. Woody, me too. It's happened to me twice, and you know what they say? That's actually really good luck if a bird poops on your head. So go us, right? You know, the second time a bird pooped on my head, I didn't even know it happened. I was walking to the subway from school, and it happened. I didn't even know, and I got on the subway, and my head felt a little. I don't think it felt weird, but I just went up to scratch my head, right, my hair, and my fingers ran into to this really weird clump, and I didn't know what it was, and then I picked a little bit off, and I saw in my fingers, I saw it was bird poop, and ooh, that was a fun rest of the ride home. Hey, Vicky. It's good to see you. Well, not see you, you know. I know I said 11:23, but I'm just gonna push it back even further because I just realized I have to heat some water up. I'm really sorry, but I promise the solutions to this will take around 5 to 10 minutes. Okay, and in the meantime, we can just chat. Just about anything, right? Siddharth, good to see you. 21 viewers, 3 likes. It's definitely what I like to see. Not hurt at all. I'm not. I'm really not. Hey, Sumaya. Hey, Gallagher. Let's tune to the page. Let's turn to the page in the meantime, right? You guys know how long it took me to draw this? Here's my first draft. It was awful. Because originally, I think every version of this problem that I've seen only shows, let's see, I gotta fix this. Yeah, it only shows this, and I think this is super abstract. It's like, oh, what is this really? It's like a U-shaped wire, and then this metal bar. What is this magnetic field, right? So I really wanted to draw this thing to show you how I would create this situation. All right, so I hope that helped make this make a little bit more sense. Okay, I'm not sure if it did or not, but that's generally one way you could draw. One way you could create this scenario. Obviously, like in a real railgun, you're not going to be using a permanent bar magnet to create this magnetic field, but I'm just showing you how it's possible. Hello, Esther. Who disliked it? What? You guys, I only can see the likes. YouTube is shielding me from the reality. That stings, man. Whoever did, I don't even know. I can't even see. One dislike, 2 dislikes. Yeah, guys. Wow. Can you guys really not? I'm gonna end the stream. This is. This is. I don't like this. I don't deserve this. Goodbye. Okay, so what do we have now? It is now past 11:26. That's totally great. Let's get started. All right, so here's the situation. The following is a very simple square-shaped, I mean a rectangle-shaped circuit with two tiny complications, right, that make it a little bit abnormal, okay? One, that it's made of two wires, so this wire here can slide forward and backwards, so this wire here can slide forward and backwards. And what that does is it makes the circuit longer, right, if you want. So as this bar goes this way, then the current's only traveling in this direction now, right? If it's here, the current's going this way. If it's here, the current's going this way, right? And it's in a magnetic field, and ours is due to a bar magnet, right? So in this region here, I have some magnetic field. Okay. It's okay. I'm not. I don't really care about the haters. Everyone's a critic. If the battery supplies a voltage of 9 volts and the resistor is rated at 2 ohms, here's my little resistor. What is the current running in the circuit? Easy peasy. That means if I use the loop rule, I gain 9 volts, I lose 9 volts here. Cool. So if I lose 9 volts and can use V equals IR, and 9 equals the current times this resistance, which is 2 ohms. Where are your units, Mr. So? Here they are. Okay. And I know my current is equal to 4.5 amperes. Yay! It's a very high current. Diamond Ninja. I keep on forgetting who you are. Who are you, Diamond Ninja? Good morning, by the way. Let's keep going. Okay. Oh no, my water's boiling. Sorry, guys. I gotta address this. Nice. Very nice. Okay. Before the circuit is turned on, the magnetic field is measured to be uniformly 3 Teslas. Okay. Pointing into the page, as is shown in this diagram, right? And if the electron current travels counterclockwise when it's turned on, that means it's going this way, okay? And in this wire, the electrons are going up now, okay? The resultant field at point A will be less than or greater than 3 Teslas. What will the value of the magnetic field at point B increase or decrease, right? So it's asking the same thing, just about 2 different points, okay? So again, since it's an electron current, I have to use which hand? Tell me in the chat, please. Which hand am I going to use? Let's check this out. Oh. The left-hand rule, that is correct. And also in the chat, can you please tell me, which rule am I going to use this time? Am I going to use this one? Oh, I'll use my left hand. Am I going to use this one? Or am I going to use this one? All right. Am I going to use this one? I call this the force one, or am I going to use this one, which is the thumbs up one? The thumbs up one, exactly, right? Way to go, guys. So what are we going to do now? Oh, look, my ink's not waterproof. That's what my tea did. Yeah, so if I use my left-hand rule, I can see to the right of the wire, the field will point up, right? So this wire creates a magnetic field that goes up. That will cancel out the 3 Tesla field here, and it'll decrease, right? Likewise, on the other side of the wire, if I use my left-hand rule, it goes in to the page, right? So this goes in. That'll add on to this field. So at point A, it'll be greater than 3, right? So the magnetic field at point A is greater than 3 Teslas, and the magnetic field at point B is less than 3 Teslas, okay? Okay, way to go, guys. I told you this would be fast, huh? C. If the circuit has a width of 10 centimeters, remember the length can change, and the bar has a mass of 25 grams, what is the force acting on the bar? This is utilizing the formula we used yesterday, where the magnetic force on any section of wire that has current on it is equal to the current traveling in that wire times the length of the wire times the magnetic field, as long as the current and the magnetic field are perpendicular, right? Okay, so in this case, I'm going to write, well, the current is what we calculated. It's 4.5 amperes. The length is 0.1 meters. And B is 3 Teslas. Whoa, Mr. So I thought you said it's greater than or less than. No. While part A definitely feeds into part C, part B was just a cool problem I wanted you to do about adding fields. It's not relevant to the actual railgun itself. Because remember, these charges in here, they will not experience their own field, right? Charges can only experience field from other charges or other external fields. So while these charges do generate a field, they don't feel it. They only feel the 3 Tesla external field that was already there, okay? So that being said, I can use 3 here, okay, for part C. And what this ends up being is, oh boy, 1.5 newtons. No, 1.35. Yikes. 1.35 newtons. Okay? All right. Now, well, why didn't you use the grams? Well, Brosafina, right? I'm getting there, right? How long will it take to reach a speed of 50 meters per second if it started from rest? All right, so let's do that. The net force is equal to ma, and this is equal to what? Let's look at my bar and the free body diagram of it, right? It experiences a gravitational force, a normal force, but then it experiences this magnetic force to the right. How do I know that? I'm going to use the other left-hand rule, right? If my current's going in this direction and my field points down, look where my thumb points. It's this way, right? So the force on this wire points this way, okay? This is exactly how a railgun works, okay, or a mass driver. These are equal. My net force is the magnetic field force, all right? So I know this is FB equals ma, and I can plug everything in now. I have 1.35 newtons equals 0.025 kilograms times my acceleration. My acceleration is equal to, okay, let's say 1.35 divided by 0.025, 54. 54 meters per second squared. Wow, this is fast, huh? All right, so if I have that, okay, now I know my other givens. My initial velocity is 0, and my final velocity is 50 meters per second. And I have my acceleration, so I can do my formula, right? I have A is delta V over delta T, or how it looks like in your Regents formula, anything, it's this. Right? Or if I want to solve for delta T to begin with, I'll have delta T equals delta V over A. And this is equal to 50 meters per second minus 0 meters per second all over 54 meters per second squared. So, whoa, okay, sorry about that. And my change in time will now equal 0.93 seconds, right? Not a long time. The projectile isn't that heavy. It doesn't have a lot of like real like applications. So if I really wanted to launch something of significant mass, I would need a much greater current, which would, and that would increase my force, right? And a much larger magnetic field, right? I would do both, and then I could really, right? Because what happens if I double my current and double my magnetic field? I quadruple my force, right? Yep. All right. And that's it. Holy moly, guys. How cool is that? So cool, Mr. So. Thank you. Tomorrow we'll have an open office hours live stream. It'll be a bit more fun. Let's try and start it at around 11:30. Okay? Thank you so much, everybody. Have a great rest of the Thursday. Yes, Monday we will learn the last thing about magnetic field, and we're going to relate it to current again. And the cool thing about what we're going to learn Monday is we're actually going to learn how electricity is generated, right? So how are all of you watching this right now? How does a power plant really work? When you guys hear about solar energy, natural gas, fossil fuels, nuclear energy, wind energy, like that's actually what we're going to be going over Monday. So it's a really cool opportunity to combine physics with environmental science and climate change, right? So, all right. Um, uh, uh, I live yearly as well, David. Have a great rest of the day, everybody.